real quick before this video actually starts. The source code for this is on itch.io, and the link will be in the description. If you enjoyed the video, like, comment, and subscribe, and I hope to see you in the next one. In the next video, I'll be showcasing how I'm going to be putting this into my game. Alright, back to the video. Hey guys, welcome. So in this video I'm going to be going over my Projective Transforming application that I made. It is made in Java, but I do plan on porting it over into C++ and C# as well. Possibly a few more languages once I learn a little bit more. So what you see on the screen right now is 4 demos so far. The first one is just moving a single point. The second one is moving the whole image, and the third one is moving 2 points, which is using a completely different algorithm. I'll go into that a little bit closer. These two are ones where you can select the image, move it around, select the points, move them around as well. So on this first image, I'm just going to blow it up here. I want you to watch the frame rate very closely. So this number right up here, it's sitting at roughly 2000. Watch what happens when I start moving this point really rapidly. Notice how it dropped down to 10,000? Now that's still pretty impressive for this image, being able to convert every single pixel. And this isn't a small image either. This is a 200 by 300 pixel image. Now of course it's not going through all 60,000 pixels, but I'll get to how that works later on in the video. Now I'm just going to go ahead and shrink this one back down just so it's not taking over. But this image right here, this one is a lot more complicated. As you can see just by blowing it up, it is reacting completely differently. Now, the way I see it, there's 3 different kinds of images really. There's the small ones, the big ones, and then there's the complex ones. So what I mean by how complex an image is really just depends on how checkerboardy it is, I guess. Best way I can put it. For example, this image you can see is very checkerboardy in very specific areas, while this image right here is not. Now I'm just gonna go through real quick on how this works, just so you guys get an idea on why this one is very simple and this one is very complex. So I'm using polygons to render these images. This image right here only has 14 polygons in it. This image has just over 60,000. So this is what I was trying to get at by how complex the image is. So let me get into how to use it now. So the first thing is creating an image. You just call it's just the constructor. You pass through the image location. For example, the string name of this is images bean or complex bean. And then you pass in the X and Y position that you want to start off with, or you can go with giving it the image location, the X position, Y position, width, and height. There's a function in there called getDefaultImage, which just returns you the default image with no modification whatsoever. The getNewImage function returns the modified image, so like what we're seeing on the screen right now. Get 4 corners returns a 2D array of each of the 4 corners. For example, array index 0, 0 is the top left corner of the X position. Index 0, 1 is the top left corner Y position. And that goes all the way around for each of the 4 points. It goes top left, top right, bottom left. Get location returns an array containing the X and Y position. Set location allows you to manually set the location of it using just XY points. Set corners allows you to set each point individually. You can pass in each point as it is, or you can pass in a 2D array. Keep in mind that it has to match the same array format that the get 4 corners provides. You can also set a single corner. The corners range from index 0 to index 3. If you go any lower or higher than that, the program will crash because there is no safety net for that. I should probably put that in. In fact, I'm going to put that in before I upload this. And then the last 2 functions is mouse-specific controls. The first one is move point with mouse, which means that it just loops over all the points, checks to see if the mouse X and Y position is over the image. You do have to pass in the mouse X and Y points, as well as the state of the mouse button that you wish to use. And same thing with the move image. The move image just moves the whole image. So let me get into how this works now. On startup, it looks through the image, creating polygons around a group of pixels of the same RGB value. That's why in the first image that I shown you, there was only 14 polygons, but in the second image, it had over 60,000. It checks to see if the pixel above it or below it, or directly to the left or right, is of the same RGB value. RG. So it does not go in diagonals. If it did, this would probably either be a lot more complicated or a lot more simple. That's one of the things that I'm going to be experimenting with. So continuing on, once it creates those polygons, it saves the location of each point of each polygon. The reason for that is because it only calculates the points that it needs. For example, it's not going to calculate a pixel that's in the center of a polygon. There's no need to. In fact, that's just wasted CPU time. So then it converts those polygons back into a PNG image. Or, sorry, not a PNG. It converts it back into a buffered image. And that's just on startup. I'll get back to the startup towards the end. When it's running, it basically repeats the last 2 steps of the startup. It only calculates the points it needs when one or more of the 4 corners is moved, and it converts it back into a buffered image with polygons. So my plans for this program, first thing I actually need to do is replace the search algorithm on startup with breadth first search. You might be wondering why I need a search algorithm in there like that, but it's just to speed it up. The search algorithm that it is currently using, I actually tested this on a real world image which was 1080 by 720. It took roughly an hour just for it to convert it into an actual image with polygons. Now, of course, once it was running at like maybe 15 FPS, but it was running. and I think that was pretty good. It converted just over 1 million pixels into 1.2 million pixels into about 600,000 polygons, which I think was pretty impressive that it managed to compress it down into half the size. I know there may be a few bugs that pop up with the current search algorithm depending on the image, so that's definitely something I'm going to be working on. I don't think that people will have that many cases of it, but on the off chance, I am going to be replacing it with breadth first search. I already have plans for how version 2 is going to work, or how I want it to work, I should say. I don't know how it's going to work in the end, but right now, the first implementation of this is the function that I just explained with polygons. I called that function pixel cluster. It just takes all the pixels of the similar RGB value and puts it into one single polygon, which is why it's called pixel cluster. I thought that was self-explanatory, but you never know.